In this training, we're going to be looking at how we can use practical work purposefully and as part of a learning sequence. So it is mentioned in the Ofsted Research and Review series for science that actually in schools, it's not always completely clear in our curriculums why we're doing a particular piece of practical work. And therefore, this means that the discussions that are then had around how effective that practical work is sometimes confused and not particularly productive. So pupils do enjoy practical work. If you ask students what's the best thing about science, they will tell you that. But research suggests that this does not in itself foster this long-term personal interest in the subject. And there is that risk that teachers are actually just prioritising those wow moments without any clear reference to any curricular goals or any particular learning. So in the EF Improving Secondary Science report, again, recommendation number 6 states that one of the key focuses needs to be using practical work purposely, linking that practical work with the other learning, and then using that practical work to develop scientific reasoning. And they've actually produced an audit tool. So considering our own practice right now, so us as a teacher or us as a subject leader, where upon this do you feel you are? Is your practical work at the moment ineffective, intermediate, or exemplary? So just take a moment now to pause the recording and consider, where do you fall within this? So obviously we would hope as teachers, as subject leads, that we want to be using our practical work as effectively as possible. So to do this, if we consider these 3 categories: using it purposely, linking it to other learning, and using it to develop scientific reasoning. I'm going to explore each of these key point areas now, and then look at how we can use this within our planning. So firstly, knowing the purpose of the practical activity is key. So purpose of practical work could be to improve that substantive knowledge of students, so that's that knowledge of that theory, or that disciplinary knowledge, that skill-based stuff, the practical element of it. So with the substantive knowledge, it could be you want them to understand a concept, a relationship, a link. For example, adding sugar to water. The outcome is that the students understand the concept of dissolving. It's not the actual process of them dissolving sugar. They do that perhaps when they make a cup of tea at home. But you want them to understand the actual substantive knowledge of what is dissolving. Whereas disciplinary knowledge is that the how, the logistics, the use and the equipment effectively. Okay, so you'll notice that the purpose of practical work is never obviously a filler for time. It's not an add-on. It's not the wow factor, because we've already seen that's not going to foster that long-term love of the subject. It does need a clear, specific purpose. And we don't always have endless time, endless budget. So we need to be thinking, well, if we are doing this practical work, what is the point of it? And it is tempting, I've got a little bit of time at the end of this week, I'll just bung in a practical. But know what is it you want students to get out of it. We need to be careful with this disciplinary knowledge, that we are developing students' skills and knowledge over time. We need to be considering, what do we expect them to have in terms of disciplinary knowledge when they get to the end of year 11 or A level? What actual skills do they need to do to be successful in those qualifications? And then students need to have prior knowledge to learn from it. So making a practical activity a discovery thing alone, research already shows, due to cognitive load, student-led inquiry based, where they just get given some equipment and see what you can find out, aren't effective. We can't expect students to discover and learn a concept by doing it in a practical. Some ideas which took scientists years to learn, it's not going to happen. It's not just going to come to them because they are physically using this equipment. So we need to be really mindful of that when we're planning the purpose of our practical activity. So this, I guess, then a moment of reflection. Is the purpose of practical work clear in our curriculums? Is there progression through the curriculum in terms of that knowledge and that skill? And are you, as a member of staff in a department, clear on that? And as a subject leader, are all your staff clear upon it? Are we actually allowing sufficient opportunities to develop students' disciplinary knowledge? Are our expectations of students' disciplinary knowledge age appropriate or appropriate within that stage of our curriculums? So I guess as a class teacher, we can be asking students, as we're in a practical, can students tell you what they are doing, why they are doing it, how it relates to the theory? Or are actually students spending too much time on the instructions, like a cookbook style, like they can't see beyond step 1, step 2, step 3, and they might point to you within that method sheet and go, oh, I'm doing this, but why are they doing that? And I guess subject leaders, as we're going around and we're doing learning walks, what do students say about practical work when you ask them? If you're in a practical, what do they say? It can be quite insightful. And it's a support and challenge in place for the variety of students within or between our classes to access that curriculum and access that disciplinary knowledge. Or do adjustments need to be made? So practical work to learn disciplinary knowledge is quite focused now at A level in particular. We've got that CPAC that we need them to follow to achieve their practical skills endorsement. But is it as clearly defined this progress within disciplinary knowledge at other stages, at Key Stage 3, at Key Stage 4? Have we actually sat down and considered it as departments? Are we correctly preparing students for this? Or is the development in students' disciplinary knowledge kind of just reliant on teacher experience and teacher questioning and teacher knowing and, having that background of knowledge within them, which as an ECT, as a newer member of staff in a school, how are they going to know that? How are they going to adjust? So our curriculums are really important for mapping that out so that every member of the team can make practical work as effective as possible. So if practical work is to actually learn substantive knowledge, research has shown that demonstrations can be really powerful for doing this. If you actually want them to learn the theory of a concept or a fact or a relationship. And this is because it can reduce the distractions of handling the equipment, recording the data, reduce that side of the cognitive load, their actual working memory of trying to deal with that, and let them focus on the actual learning you want them to be doing. And actually, research does show that students can learn better from demos rather than videos because of the high quality questioning that a teacher puts in place alongside it, which is obviously lacking sometimes from the video. And questioning has been found to be a really crucial part of making practical work as effective as possible. But it doesn't just have to be demonstrations. Practical science does include that use of simulations. So the University of Colorado Boulder, they've got these excellent ones, which I'm sure you may have already used some of them. So they're a great place where students are able to alter some of the variables within a practical, get different results, actually collect live data themselves. And they can go through all the practical parts of an activity, but without that cognitive load of having to deal with the equipment, move around the classroom, get distracted by other students that are also there trying to get this piece of equipment, share that piece of equipment, and they can actually concentrate on the learning that your practical work is trying to develop without some of those other things going on. So the next point to consider is sequence of those practical activities. You know the purpose, but how does it then fit in with the other activities that exist? So we need to be clear about the skills and knowledge you're trying to develop, then thinking about the best approach to develop these things and sequence it within what they already know. So it's unreasonable to expect that lasting learning of a scientific concept is going to occur from a single relatively brief practical activity. Practical work is an important string to our bow, but as a successful science teacher, it needs to come alongside other activities. And then we need to be using this practical work to develop students' reasoning. So one of the fundamental things of scientific reasoning is this idea of, control variables, precision, validity of experiments, and indeed performance on control variables tasks kind of often in written exams. So that's where students kind of fall down on, and that's where we need to be taking these opportunities when we're doing practicals, when we're doing video demonstrations, actually discussing control variables, making it explicit to students within practicals. And it's also important to give students the actual practice of controlling some variables within their own experiments, but we need to plan for these activities. We need to know what the purpose of the activity is, and sometimes the purpose of the activity could be the outcome of this ability to do scientific reasoning. And sometimes it might not be planned, but experiments do go wrong, and then we can use this for our excellent teacher questioning to explore this and take this as an opportunity to develop some of this scientific reasoning for students. So it leads us back to our audit tool for the EF and what makes exemplary practical work. So I'll just leave this there for a moment for you to just reflect upon where are you at this point in ensuring this. So let's consider mapping out practical work for a particular topic. So on the left-hand side here, you'll notice the key learning questions, the key constructs for a particular topic at Key Stage 3. So for each of these key constructs then, there are defined outcomes as part of the scheme for learning, which forms part of the wider curriculum. So this first key learning question, what's the difference between a pure substance and a mixture? We can see one of the key outcomes would be to identify pure substances using melting point data. So if we use the EF audit tool and use their side headings to structure our thinking, what's the purpose? How does it link with other learning? And what opportunity is there for developing scientific reasoning? Well, the purpose of this particular practical, if I choose to do it as a class practical, would be that students can identify pure substances using melting point data. So that is the substantive outcome I want. I want them to have this fact that they would then be able to move forward and use in other ways. So how does this link to that other learning? Well, in other topics, they have learned about heating substances using a Bunsen burner. Later on in this topic, they're going to need to be using evaporation to separate a mixture. So perhaps at this point, maybe it's an opportunity for doing a demo of heating techniques as a refresher from earlier topics, such as using a Bunsen burner, and with high quality questioning, make sure that all students can retrieve that information, and that I'm going to be confident that they're all going to be able to complete this task without being overloaded by the actual step-by-step of heating a substance up to determine the melting point. So, for example, using thermometers correctly, using the Bunsen correctly, heating safely, using the safety equipment. Then I think about developing scientific reasoning. Well, there's an opportunity to. We can talk about control variables if we want to compare different substances, perhaps. And again, that could come through from my high-quality questioning. So perhaps for this particular key learning question, the practical outcome would be that a class demo would be useful. So if we take then the next key learning question, what happens when a substance is dissolved? Here are the intended outcomes defined on the scheme for learning, part of that wider curriculum. So if we look at the one in yellow, describe the change in mass when a solution is formed. So again, we've got our key thinking areas, the purpose of this practical work, how does it link with other learning, and is there opportunity to develop in scientific reasoning? Well, the purpose of doing this practical is I want them to learn a concept again. I want them to know that mass is conserved when a substance is dissolved. And I need them, therefore, to be able to mix a solute and a solvent and identify the point at which it has dissolved, using and handling that classware correctly. So how is this going to link with other learning? Well, they're going to need to be able to measure mass. They're going to be able to record, they need a way of recording the results in a suitable way. So knowing the mass before, the mass afterwards. They're going to need to know the difference between a pure substance and a mixture. They're going to need this knowledge of particle model. So I've got to start considering, well, what are some of the barriers here? Do students know how to use a balance? Do students know that they're going to need to take the mass of the beaker to determine the mass, a way to determine the mass of the solution? Do they have the skills to do that? Are they able to record the results themselves? Are they going to be able to follow multiple steps? Do they know how to measure the volume of the solution, of the solvent they're going to be mixing in? Do they know how to measure mass correctly? So I might at this point think, well, class practical would be good, because we're going to be going on to later on in this topic look how temperature affects solubility. So I need them to have this skill of knowing what a dissolved substance actually looks like, not just understanding the idea and the substantive knowledge of what it is. And I need them to be able to use that glassware safely to be able to do that. So I would do a class practical. What that scaffold would look like within that class practical could differ between different groups within the same year group, depending upon prior experiences and prior knowledge. But the outcome at this point would seem suitable, that it would be a class practical. So if we consider the next key learning question, how does temperature affect solubility? So here are the intended outcomes on the scheme for learning. And it does clearly say it is to plan a practical to investigate the relationship between temperature and solubility, plus a graph, and reach a conclusion. So at this point, the purpose is very clearly the ability to plan. So it's that scientific reasoning I'm hoping to develop and for students to gain from this particular key learning question and the outcomes from it, the ability to plot a graph and reach a conclusion. So it'd be very easy to look at the key learning question for this and to look at this, look at this topic and go, right, great, doing a practical next lesson, we're going to look at how temperature affects solubility. That's not actually what we're wanting students to get from this. And this highlights the importance of the aspect of the role of practicals within our curriculum design as a department, and having a shared vision of what are the outcomes, what is the purpose of practical work, at what point are we developing different skills in scientific reasoning, different skills in disciplinary knowledge, and maybe in this particular instant, we want them not actually doing the practical is okay, because a virtual simulation would allow them to, they could plan it, get the outcome that I want from that. They could then do the virtual simulation, collect the data, but focusing on that ability to plot it, of collecting the data in order to be able to plot a graph, considering what data it is they need to be collecting. Then they can plot the graph and reach the conclusion. So in this case, that might be most appropriate. So one of the things that we've developed using examples of different ways different schools are doing this across the country is actually mapping out what working towards expected, above expected looks like in different practical and scientific reasoning skills throughout our Key Stage 3 curriculum, so that staff can be confident themselves when deciding whether to do a demo using a simulation. What prior knowledge students have, what skills that we can expect them to have, what are we trying to focus on and develop them. So now consider for a topic that you are teaching or about to teach. What practicals will you be doing within this topic? What is the purpose of those practicals? Is it to develop substantive knowledge or disciplinary knowledge? How does the knowledge and the skills you're expecting students to use within that practical link to their prior learning? How does it link to their future learning? Are you being realistic with the practical skills that you expect students to have, that disciplinary knowledge, their ability to measure volumes, to use glassware, to heat substances safely? And then what's the development of their scientific reasoning? Is it planned for? Will it be an unintended outcome if it happens? Is the practical as a class practical the best way to develop that? Do you want to develop that? Is that the right purpose of that practical? And consider these 3 questions for this particular topic. And then consider, are your answers to those related to your scheme for learning that you are following? Is your approach the same as every other person in your department's approach? Or is the purpose that you are doing a particular practical different to someone else's? And then that's going to make the second part, How does that practical link with their other learning? Very difficult for staff to predict for as students change classes, as students move from one teacher to another through different years of their science career at your school. And then does that mean that developing their scientific reasoning then falls through the gap? So what is the purpose of your curriculum in ensuring that these things don't happen? Has practical work been planned as precisely as perhaps the development of the key learning questions and that substantive knowledge that you are hoping to develop and embed within your learners? Thank you for listening.